Okay, so this lesson adds another layer onto what we've been working on with linear inequalities by adding what's called um, an objective function. So here's the same situation that we've been working with for a couple of classes now. We've got a bakery, and our bakery owner is selling muffins and cupcakes. Okay. And what we learned last time was that if we write an inequality to express certain rules about how many cupcakes and muffins she makes, then those sort of graph as not just lines, but as zones on the plane. Let's see what we're talking about. So for example, we said that Mrs. Gallus's cupcake tins, her trays, only have room for at most 60 muffins and cupcakes, right? So what we realized that muffins plus cupcakes, well, that can't be any bigger than 60. So we have our first constraint here, m plus c less than or equal to 60, which I'm going to draw in red. When I draw that, when I graph this, either with Desmos or a calculator, or by turning this into an equal sign and figuring out which side I need to shade, I end up with a zone that looks somewhat like this. Okay. So for example, so anything in the red zone here fits into our muffin trays. I'm going to erase this just for now, but it's just going to be on this side here. Okay, let's try our next inequality. Mrs. Gallus needs at least 20 muffins. How can I write that? Well, that just simply means that m is going to be greater than or equal to 20. Well, how do I graph m greater than or equal to 20? Well, if I change this to an equal sign, then I would see that m just equals 20, which on our plane is a vertical line here at the 20 line. And so all of the points to the right of this would be shaded green. I'm not going to do it now because it would make the visual a little messy, but that would be that zone. And I need at least as many cupcakes as I need muffins. Okay, so what that means is my number of cupcakes has to be at least bigger than my number of muffins. How does that graph? We'll graph that in blue. And what we'll see is that this is simply this line here up on this side. So you can see that if we're on this side of the green, the bottom side of the red, and the left side of the blue, we're actually always inside this little triangle here. This is our feasible region. So in this region are all of the solutions to this system of inequalities. So what are some points that are in this system, that are in this region? Let's just take a look. Well, I mean, this one looks pretty good. So let's see, this would be 25, 20, maybe 30. So 25 comma 30. And remember, this is just like muffins, cupcakes. So 25 muffins, 30 cupcakes. Yeah, seems reasonable. How about over here? Maybe 20 muffins, 30 cupcakes. Maybe 20, 30. How about that? Can we be on the corners? Yeah, sure, because these are all solid lines. Solid lines are part of the region that they boundary. Okay, so here, how about 20 comma 20? All right, that's fine. So 20 comma 20. All three of these are solutions. Right. Now we're supposing that Mrs. Gallus sells the muffins. The muffins are $2.75 and the cupcakes are $3. Okay, so we haven't talked about money at all yet, right? But now we're going to sell them for $2.75 for a muffin and cupcakes for $3. So for each of these solutions, let's find the revenue, the money that we're going to make for each of these. Let's start with 25, 30. So I make 25 muffins, 30 cupcakes. Well, that's not so hard. Well, it's just going to be 25 times the price of a muffin. That's 275. So 275 plus 30 times the price of a cupcake. So that's 3. So let's see. I'm just going to put that into my calculator here. 25 times 2.75 plus 30 times 3. That'll give me $158.75. Okay. How about 20, 30? 20 comma 30. So 20 times $2.75 plus 30 times 3. 20 times 275. Whoops. This will be $145. Okay, not quite as much money, but that's fine. How about 2020? 2020. Well, this probably won't make nearly as much money at all. So if I run the calculation again, but this time with 20 of both, I end up with $115. Okay. Well, that's not quite as good, but that's still fine, right? We're still in the constraints. We're still following all of our rules. But watch what happens when I find the corners of this shaded region. Well, I've already found one. 2020 is one of our corners, right? So let's just highlight that. 2020 is already a corner. Okay. There's 2020 right there in green. What are the other corners? Let's take a look. Let's scroll up a little bit and find them. Okay. Well, it looks like we have 2040. So 20 muffins, 40 cupcakes, and 30, 30. That's another point there. All right. Why don't we add those to the table because those are solutions after all. Those are solutions. Why are they solutions? Because they're on solid lines. Again, right? Solid lines are part of the boundary of the region that they boundary. If it was a dotted line, it wouldn't work. And why are they solid lines? Because these all have equal signs on them. Greater than or equal to or less than or equal to. Okay? So let's try that. I'll add that now. 30, 30, and the other one was 20, 40. Okay? Now let's find the revenue for those guys. So how much money would we make if we made 30 of each? So I'll just repeat my calculation. 30 times $2.75 plus 30 times 3. For a revenue of 172.5. Okay, that's actually the best we found so far. But now let's try 20 muffins, 40 cupcakes. 20 muffins, 40 cupcakes. And now look. If I plug that in, I get $175. That's the most money we have so far. So far, it looks like the most money I can make is $175. And notice that that happens at a corner of the triangle. Okay, 2040. That's up here. Meanwhile, there's a third vertex over here, 3030. Okay, so these are the three vertices. Or vertexes. Okay. And what we found is that the most revenue occurs at this corner and the least revenue occurs at the green corner. Okay, so what's going on here? What we've just discovered is something called an objective function. An objective is a goal, right? So like the objective of any game is to win the game. So the objective in a game of soccer is to get goals into the net, right? The objective of a 100-meter dash is to complete the course in the smallest amount of time, right? The objective of most businesses, for example, is to make money. And that's the case here. We're trying to make the most money. And so on top of all of these rules we have to follow, we're adding a new layer. How much money can we make? What's the best point inside of this feasible region that gives us the most money? Okay. So here's a new example. A farmer can plant up to 120 acres of soy and corn. I'm going to start highlighting these constraints as we go. So 120 acres of soy and corn. So up to 100 acres of soy and corn. Let's highlight that in green. Okay. Now the farmer has to plant at least 38 acres of corn. So I'll highlight that in blue. At least 38 acres of corn. That's because of pre-orders of corn. Each acre of soy costs the farmer $35 in investment crops, and each acre of corn costs $20 in investment. And we have $3,000 to spend. All right, so let's use maybe a light purple highlighter here. And we've got soy costs 35, corn costs 20, and we have $3,000 to invest into crops. Okay. And then finally, we have what's called our objective function, which says that when we sell these crops, we're going to make $80 for each acre of soy. So when sold, soy will earn 80 and corn earns 50 in revenue. And this is our objective function. It's really important not to confuse the objectives with our constraints. Objectives are not constraints. Constraint. Okay. What do I mean by that? Well, let's just see the difference between each, right? Let's create an objective function. So what is our objective function? What are we actually trying to optimize? Well, here it's revenue, right? We want to make most money. And so the money that we earn can be expressed as like a mathematical expression. So here, for example, if we have X soy, X acres of soy, and Y acres of corn, then the revenue we earn is just going to be 80Y, 80X, sorry, plus 50Y. Right? This is just our revenue. This is our money. Cha-ching. Okay. This is what we're trying to get the most of. Our constraints, though, are what's limiting how much we grow. Because like if all we wanted to do is just make infinite money, we'll just like plant as much of the most expensive crop we can. But we can't do that, right? We have to have at least 38 acres of corn. Okay. So we also have to draw our constraints just like before. So our first constraint here is in green, which I'm going to actually draw in green. I can only plant up to 120 acres. That's only how big my field is. It's right there. So that means that my X plus my Y, it has to be less than or equal to 120. Right? That's my first constraint. Note how I didn't like include money anywhere in this. This is just has to do with acreage. Okay, I could call this my space constraint. My next constraint says that I need at least 38 acres of corn. So my corn has to be at least 38. It has to be greater than or equal to 38. This is due to pre-orders of corn, right? I could call this like my pre-existing arrangements, maybe my orders. My orders constraint. And then finally, every acre of soy costs 35. Every acre of corn costs 20 and I only have $3,000 of investment capital to spend. Okay. Don't confuse these expenses with revenue. So that means that the amount I pay, well, it's going to be 35 times however much soy I plant plus 20 times however much corn I plant. And well, that can't be any bigger than 3,000 because that's all the money I have to spend, right? This is my budget. Buget. Budget. Just like before, right? Just like before, each of these will create a zone on the graph, a region on the graph. So just like this constraint created this red region that we would have shaded here, each of these is going to create their own region. So for example, x plus y less than 120 will shade in everything to the left of the green line. C being greater than 38, well, here's my C equals 38 line, and C being greater than that means I go above my blue horizontal line. And my costs being less than 3,000, well, that's represented by this purple line here. And I know this is getting really busy. This is getting really messy, but so I'll change this in a second. But that will shade in this region here. And what you might notice is that there is a region in the middle here that is triple shaded. Okay, it's this little quadrilateral. So I'm going to erase this whole thing and just shade in the triple shaded region. Okay, this region here is my triple shaded region. And I can see that it has 4 corners. Now, we're not going to prove this in this class. But if I go now back to my objective function, how much money I'm going to make, 80x plus 50y, this is how much money I'm going to make, right? The maximum and minimum of this function, they will occur at the corners of my triple shaded region. And we're not going to prove why that's true. All right. But what that means is all you have to do now is just look at each of these corners and just run the calculation. All I have to do is run the calculation and see how much money will I make if I make each of this, if I plant each of this. So let's try one. 0, 120. So that would be 0 soy, 120 corn, right? Because this is soy, and then over here is corn. Okay, well, soy is sold for 80 each. So it's going to be 0 times 180 times 80, sorry, plus 120 times 50. That gives us a revenue of 6 grand. Not bad. How about if I only do 38 acres of corn and no soy? This doesn't seem like a smart move, but let's just try it. 38 times 50. Well, that only gives me $1,900. That's not nearly as much. I want to use all of my field space, really. Well, let's try these other 2 points. What if I just still do 38 corn, but then I fill up the rest of the field with soy? 64, 38. Okay, so 64 times 80. 64 times 80. This is my revenue. plus 38 times 50. Well, this gives me $7,020. Okay, now we're making money. But now let's try the last corner. Where is it? It's 4080. So again, we'll do 40 acres of soy for each, $80 each, plus 80 acres of corn for $50 each. And I end up with a revenue of $7,200. So I can now see that if I want to make the most money, I have to plant 40 acres of soy and 80 acres of corn. That's a lot of different information. We have objective functions, constraints, graphs, shading, and then having to check all of the corners. It's a long process, but once you practice it, you will get better. So pause the video here before you try the check your understanding questions, and I'm going to go through them now. So Sammy's making string bracelets to sell as a fundraiser. It only takes her 10 minutes to make a jellyfish bracelet, but 30 minutes to make a zigzag bracelet. Okay. Now she wants to have at least 25 bracelets ready to sell, but she only has 8 hours to actually work. We have J is the number of jellyfishes, Z is the number of zigzags, and her jellyfish bracelets sell for $2. Her zigzag ones sell for $4. Okay. So already we can see both constraints and an objective function. But let's go through this bit by bit. If Sammy only makes jellyfish pattern bracelets, what's her maximum number she can make? Well, 8 hours is 480 minutes. So let's just convert it into minutes. And every minute, every bracelet takes 10 minutes to make. So 480 divided by 10, that's 48 bracelets. Okay? So that means that if she makes 80 bracelets, if she makes only jellyfish bracelets and no zigzag bracelets, she can make 48 of them. Similarly, if she spends all 480 minutes only making zigzag bracelets, well, 480 over 30 is 16. Okay, so she can make 16 zigzag bracelets. So her time constraint will look like this. And her feasible region for time is inside here. This is like our budget, our time budget. Okay? This constraint, it doesn't ask us for what this inequality is, but this is simply 10J plus 30Z has to be less than or equal to 480. And you can try putting that into your calculator to confirm that that's what that looks like. Meanwhile, she also wants to have 25 bracelets to actually sell. Okay? So that just means that the number of jellyfish bracelets that she makes, plus the number of zigzag bracelets that she makes, it has to be bigger than or equal to 25, right? What does that look like on the graph? Again, you can ask your calculator, or you can just graph it. If you don't know how to graph it, it's definitely worth checking up on and like seeing. Okay. So there's our boundary line, and I want to be bigger than 25, so it's actually all of these points here. And I can see now my feasible region for my two constraints is this triangle. Now let's write a function for profit. Profit does not show up anywhere on this graph. It's not there. Instead, we need to look at our original question and say, oh, the profit we make is just 2 times our jellyfish number plus 4 times our zigzags. This is our profit. I'm not graphing this, okay? Because profit isn't a variable on my graph. I'm not graphing this. Sammy's now considering making 18 jellyfish and 8 zigzags. Does this work? Well, if I zoom in on my graph, I can see that 18 jellyfish and 8 zigzags is just barely inside of my feasible region. 18.8 is right there. So yeah, we're just on the cusp, but yes, it is in the feasible region. And we can see, right? I can just plug this into my original question. And like, do I have time to do it? Well, yeah, right? 18 times 10 minutes for each jellyfish bracelet. Plus 8 times 30 minutes for each zigzag bracelet. Okay. Well, that's just 420 minutes. Okay. That's 7 hours. We have 8 hours to work with. She has time to make that many. And if she makes 18 jellyfish and 8 zigzags, this is 25. This is 26 bracelets in total. So it is more than 25, right? Because she wanted to have more than 25 bracelets to come and sell. So we both have time and it's enough bracelets. So yes, it is doable. How much profit will she make doing this? This is again pretty easy, right? Well, every jellyfish bracelet is just $2, right? So it's just gonna be 2 times 18, and every zigzag is worth 4, so it's just 4 times 8. And that's $68 for 7 hours of work. Not sure if I'd take it, but well, there you do you, right? And is this the most profit she can make? Well, logically, you can kind of see, no, she still has time. So she could make some more bracelets. However, I can also know just by looking at my graph, this point, it's close to a corner, but it's not on a corner. And we know that our objective functions hit their maximums and minimums on the corners, right? So in order to check what the maximum profit actually is, we would have to check all 3 corners to see how much we can make. Okay? Now I could do that, right? I could do that, but then I would have to solve the system of equations to find this intersection point. I don't particularly want to do that. Okay? So instead, we're just going to try and apply some logic here. A jellyfish bracelet takes 10 minutes to make and earns her $2. The the zigzag ones take 3 times as long to make. But they don't make her 3 times as much money. They only make her twice as much money. It's more efficient to just make as many jellyfish bracelets as she can. She should just make jellyfish bracelets. It's the best use of her time. So logically, which of the 3 corners maximizes profit? It's this one, 48 jellyfish. And how much will she make if she's able to make and sell 48 jellyfish bracelets? Well, each one goes for $2, which is 96. For 8 hours of work, that seems a little better. So this lesson adds one more layer on top of these systems of inequalities. In addition to being able to find our region, our like multiple shaded region, we also need to check the corners to see which of them maximizes an objective function. And the easiest way to mess up on these questions is to mix up our objectives with our constraints.